Throughout this chapter, we're mostly going to be focused on techniques for finding indefinite integrals. That is, integrals where the answer is a function versus definite integrals where the answer is a number. And one reason for this is that most of the work in finding a definite integral is first finding the indefinite integral, right? Then you just substitute the limits into that function and you do some careful arithmetic. The second reason is that we're going to spend a lot of time looking at definite integrals in the next chapter when we start talking about applications of integration, so you get plenty of practice with those eventually anyway. Now, as we go along, you're going to see that finding indefinite integrals, sometimes even of functions that look relatively simple, can be a messy process, if it's even possible at all. Now, one approach to finding these integrals is to use what are called tables of integrals. These are lists of integrals and their solutions, usually with some parameters to make them as general as possible, that you can use to find results for specific integrals that you're trying to find if you can find one in the table that matches the one that you're looking at. So over the course of the chapter here, we'll actually derive a number of these results so you can see where the formulas come from. Now, most textbooks leave this section until the very end. And I've always assumed that this was because authors didn't want students to know that there were shortcuts out there that could essentially do their homework for them, right? Get you out of doing a lot of those messy kinds of calculations. So the material here is intended, at least in part, for students who are studying on their own, which is why we chose to present it right here at the beginning. For students learning independently, these are great resources both for checking your work and sometimes for getting a hint about what method you should try using if you're stuck on something. So I have here uh, three of the kinds of things you would see in a table of integrals. Right? You notice how we've got the a's and the b's and the n's in here. Those are the parameters that I was referring to on the previous slide. So what I want to do is I want to use these to find that integral on the left, the integral of x over 3x minus 1 dx. The first step in using these tables is to see if you can find a match. Right? I've listed three entries here, and only one of them actually is going to match up with this integral that we're trying to find. So if you look at the first one here, you might be tempted by this because if n was negative 1, then this would become x over ax plus b, which is very similar to our integral, right? But you got to be careful. There is this restriction over here that this formula does not work when n is equal to negative 1. And yeah, okay, really, if you think of that through, that does kind of make sense. Because remember, back when we learned the power rule for integrals, right? Remember that was this thing. That also didn't work for n equal negative 1, and that was kind of a special case where the answer ended up involving some logarithms. So, okay, that makes sense, and it rules this one out. Right? That's not the one we're going to want to use. Now, these next two, they both have this negative, they don't right up front look like our integral, but they both have these negative exponents, right? So this one would be the same as 1 over ax plus b, and this one would be the same as x over ax plus b, right? And this is one of those fussy math cases where you got to be really particular. Our integrand has that x up in the denominator, excuse me, up in the numerator. And this second one here does not have that. So got to rule that one out. And this this last one is the one that we're actually going to use. So the next step is figuring out what these a's and b's are. Right? It's kind of matching up the parameters in the formula with the numbers in your actual integral. So if we take a close look here, if I put a 3 in here for a, and a negative 1 in here for b, and of course move that negative exponent down to the denominator, right? Then the formula here would exactly match my integral, right? So to get my answer, I'm going to put 3 in here for a, and negative 1 in here for b, and I'm going to do the same thing on the inside here, and there you go. That's almost it. Let me write the whole thing. Put my integral over here on the left. And that's almost it, but we can clean this up a little. This is x over 3 plus 1/9 log absolute value 3x minus 1 plus c. And there's my answer, right? Not too much trouble, right? Not too hard to do. And like I said, as we go along here in this chapter, we'll take another look at ones just like this and see where this formula comes from. I have a second example here, and this one is a little messier, right? But it's the kind of thing that comes up, right? So we need to have a conversation about it, I think. So first, you notice that this does match, right? I have an x squared, and I have a number minus x squared. Okay. But the one on the right, the formula, doesn't have a number in front of the x squared, right? There's only the one parameter, and that's the a squared over on the left. So, but that's okay, because I can get rid of that 2 in front of the x squared by factoring it out. Right? I'm going to make this the integral dx over x squared square root of 2 times 5 minus x squared. Okay, so that's progress, right? Now I don't have anything in front of that x squared. And I'm actually going to bring that square root of 2 all the way out of the integral. So make this 1 over the square root of 2 integral dx over x squared square root of, and let's hold here, right? This has a squared, and I don't have something here. All I have is that 5, right? But I can make it look like that. What I'm going to do is I'm going to write this as the square root of 5 squared minus x squared. And now I have a match, right? A is going to be the square root of 5. Right? So if I come to the formula here, right, this is 1 over the square root of 2. And all I'm going to do is I'm going to replace all those a's with the square root of 5. And just to make this go a little quicker, right, you know, since a is the square root of 5, a squared is just 5. So this is going to be, well, don't lose that negative sign. Let's put the negative out in front here. Negative square root of 5 minus x squared over 5x plus c. And I really can't clean this up, right? Let's distribute the one over the square root of 2 in here. This is negative square root of 5 minus x squared over 5 square roots of 2x plus, now look what we're going to do here. I'm going to take 1 over the square root of 2, which is a constant, and I'm going to multiply it by a constant. Well, that just gives me a new constant. Now, a lot of times you'll see people, they'll just go ahead and write c there and understand that, yeah, okay, technically it's this divided by the square root of 2, but a constant is a constant. I'm always a little uncomfortable reusing a variable like that, so I would put a different letter there. I just call it d instead. Okay, now, yeah, okay, technically we're not quite done yet because of that square root of 2 and the denominator. We really need to rationalize this, and if we do, this is going to become negative square root of 10 minus 2x squared over 10x plus that constant d. And you notice how that 10 minus 2x here crept back into the answer, right? And you'll see as we go along, it's not uncommon for that to happen when we're looking for these kinds of indefinite intervals. Okay, so that's the basics of using tables to find integrals. In the next lecture, we're going to look at another kind of thing that you find in tables of integrals, but it's slightly different. It's something called a reduction formula. And it doesn't take your integral and turn it into a function per se. It takes it and turns it into a function that still has an integral in it, but an integral that hopefully, anyway, is going to be easier to find than the one that you originally started off with.